Hello everyone, I hope you are doing well. My name is Asma, PhD student in Sultan Moulay Slimane University. I share with you today my work on risk assessment of groundwater droughts, and I thank you in advance for your attendance. To do so, I am going to start first by putting you in the research context, second, the study area, third, introducing to you the climate and anthropogenic analysis, then the drought risk modeling, and last, a conclusion and outlooks. Let's start by the research context. The importance of this issue is due to stabilizing awareness among both the public and the scientific community regarding the sustainable exploitation of groundwater as an important source of fresh drinking water and other uses, of course, such as irrigation. Taking into consideration the climatic variability that has always been expected, the pressure caused by the demographic explosion in the world and in the studied area specifically, which is mainly due to its economic development, such as the food industry setups, the development of roads and highways, as well as the installation of some big poles of industry. These are all factors that increases the water demand in a spectacular way, giving rise to a series of effects and problems. One of these problems, and probably the biggest, is droughts. Groundwater droughts can result from reduced recharge over a prolonged period of time, or an excessive discharge. In fact, the resources themselves may at first glance appear to be unlimited, and the signs of their depletion may not be distinguishable from their normal fluctuations over time. So the complexity of ecosystems often makes it difficult, even for an expert, to predict the consequences of changes brought about by climatic conditions and human activities, which gives rise to risks of droughts that threaten the satisfaction of current and future needs. So the aim of this work is to quantify and make readable the current situation of the studied aquifers in terms of water table situation and risk scenarios, and also highlight the impact of climate variability and human activities on the aquifers. For this, a methodology is used in this work in order to investigate the current climatic situation in the studied area, and of course the impact of climatic change and anthropogenic activity on groundwater resources. On one hand, the anthropogenic activity is assessed by land cover's evolution over time, from the year 1984 to the year 2017, especially the evolution of permanent vegetation that requires irrigation. On the other hand, the assessment of climatic change is based on precipitation trends analysis and modeling the groundwater depth using groundwater drought indices and reliability analysis. Therefore, a couple of indexes were used, such as Standardized Precipitation Index and the Standardized Groundwater Level Index. The drought risk modeling itself was done by a methodology developed by Sina SADEGHFAM that introduces groundwater drought risk indexing using the reliability analysis. This strategy is neither an inferential statistical technique, black box model, nor a distributed model. It may be regarded as a gray box model. In fact, as a matter of principle, for a system to fulfill its requirements, reliability is defined as the probability of the system remaining operational, which means the non-failure probability. And risk is defined as the probability of failure. Both assessed by considering the interactions of load and resistance, based on probabilistic analysis, of course. The pivotal notions here are as follows: the load and the resistance. Load accounts for external effects in terms of groundwater depth, the GWD, measured from the ground surface at the local observation well, and therefore, the greater the GWD drawdown, either the less the recharge or the greater the pumpage, both external effects. Now, resistance is the system's ability to cope with external effects. Now, the system as a water resource is reliable when the load does not exceed the resistance. If the load exceeds the resistance, the system is unreliable and hence its performance is at risk. The studied aquifers are Beni Amir and Beni Musa that are part of the multi-layered Tadla system. This area is in the Tadla plain. The latter is located in the center of Morocco, north of the High Atlas and west of the Middle Atlas. It is demarcated in the northeast by the plateau of phosphates and in the southeast by the Atlas of Beni Millet. Now let's start our statistical analysis. This part requires collecting data of several meteo stations in the study area. There were 4 stations implicated in the study: Beni Millet, Mishra Taht, Moulay Bouskri, and Oued Sidi Idriss. The precipitation data for each station were obtained by the Bay Hydraulic Basin Agency. The following graph shows the annual moving average precipitation over a time span of almost 50 years. The precipitation trends records at the station has the same pattern of regressive and transgressive periods, with a different range of values. This difference might be explained by the spatial distribution of these stations, since the Beni Millet and Sidi Jaber are located in the piedmont of the mountain, where the altitudes are relatively higher, while the rest of the stations is located in the northern part of the plain, where the altitudes are lower. From this time series, we calculated as well the standardized index of precipitation next. Let us take, for example, the station of Sidi Jaber. The graph presents on the axis of the x the years and on the axis of the y the values of the SPI. This latter varies from -2 to 2, with the negative values are those corresponding to the dry periods and the positive values are those corresponding to the wet periods. The alternation of these periods in time is quite remarkable. Besides, the length of the dry periods is higher than of the wet periods. The dryness itself is of different intensities, namely years like 1996, which knew an extreme dryness, while for example the year 1991 is moderately dry. The wet periods also presents this kind of heterogeneity. Let us take, for example, the station of Sidi Jaber. The graph presents on the axis of the x the years, and on the axis of the y the values of the SPI. This latter varies from -2 to 2, with the negative values are those corresponding to the dry period, and the positive values are those corresponding to the wet periods. The alternation of these periods in time is quite remarkable. Besides, the length of the dry period is higher than that of the wet period. The dryness itself is of different intensities, namely years like 1996, which knew an extreme dryness, while for example the year 1991 is moderately dry. The wet periods as well present this kind of heterogeneity. In the same way, this alternation and these variabilities are observed at all the stations implicated in the study. Regarding the land cover analysis, it was done using a series of Landsat images. The results of the calculated indexes, the NDVI, NDWI, and NDSI, as well as supervised classifications, presents remarkable heterogeneity. Next, let's talk about the groundwater drought risk analysis. A network of 34 piezometers with following spatial distribution was implicated in the study. The temporal evolution of the piezometric level shows a remarkable drawdown. We caught, for example, a lowering from 20 to 10 meters in the perimeter of Bnei. Using these series to calculate the standardized piezometric level index, we obtained the following results. The SWI index also varies from -2 to 2, but this time the negative values are those corresponding to the normal state of the water table, while the positive values represent the state of dryness of the water table. It can be noticed that the recent part of the time series is the one affected by the dryness, illustrating, for example, the situation related to the year 2017. We can notice that the part towards the center has suffered a severe dryness, while the part towards the Piedmont is more or less moderate, and the part towards the north of the plain is moderately affected. Now, let's talk about the results of the GDR, the Groundwater Drought Risk Modeling. The results of the model are, as summarized in the table, the Reliability Index, the GDR, and the Environmental Hazard Index, EHI. In terms of GDR, it is perfectly clear that the southern part, the Bnei Musa aquifers in particular, suffers from serious drawdown of the water table. The area's resistance, on the other hand, is not seriously stressed toward the northeast, but the aquifer is stressed toward the north, the southeast area and downstream of the aquifer. At this stage of the study, the variability is measured in terms of risks during the first and the second half of the time series. This is taken as an indication of accelerated risks measured by the EHI. So to sum up, for some observation wells, GDR values are high, but the EHI values are low. In these wells, variation during the either 70 years are insignificant. These observation wells are likely to suffer from groundwater drought in the dry seasons, but likely to be replenished for the next year. GDR and the EHI values are affected by precipitation and abstraction, and these are reflected in the recorded time series of the water table. But these results are not final yet. This is caused by the lack of information, and when I say lack of information, I mean shortage of time series. This latter is due not only to the weakness of the meteo stations and piezometric networks, but also to gaps existing within the time series in hand. And since the majority of time series I used have exactly the same kind of gaps, it has become necessary to elaborate fill-in methods that does not rely on the same information in a neighbor source, but on an entirely different kind of information that may have a causal relationship with the information to predict. So as perspectives and outlooks, the next chapter of the study is going to be dedicated to fill in time series gaps using AI methods, since gap filling is often an uncertain task and there is a wide range of techniques such as the nearest neighbor, linear regression, multiple linear regression, etc., etc. And again, given the circumstances of my study and my data, I think that the fuzzy logic represents the most convenient way to do so. So to sum it up, I would like to thank you for your attendance, and I would like to thank the organizing committee for this amazing opportunity, and also I welcome any question or suggestion from you. Thank you.